Hi, I'm Jack Carl, and this is my Week 7 MATLAB composite body project. We deal with solving for a deformed area and volume based on a defined deformation map. I like to start with my results so you can see my geometry and see what we're working towards. This is my original geometry. I apply a deformation map that has to do with cosine, and so you'll see it's symmetric around the x1, x2 plane, and that was my goal. We solve by hand one of the area transformations and one of the volume transformations. We deal on both of those. We're dealing with this top frustrum. We deal with this area at the top deforming to be this area seen here, and we deal with the volume of that top frustrum and how it changes as well. First, we look at our deformation map. For this one, we take it's just the deformation field we've been using in previous weeks, or I've been using in previous weeks. Here is my final deformation map, and for Z1, Z2, and Z3, we apply the specific geometry of each body. So here, this is more having to do with last week's code and assignment, but we took our body 1, we took that deformation vector, and here is our geometry given, and we apply that, and that's how we get both our F map and our deformation map. Similarly, for body 2, the rectangular prism, we do the same thing. We take that rectangular geometry, we put it in the deformation map, and then we create that matrix F. This is the important body. This is the one that we will be looking at in the next couple steps for the area and the volume. This is the parametrization of that frustrum. These are the tangent vectors to the faces, and then this is the map that we deal with, and the F value that we deal with. So, first let's look at the deformed area. So I started off by trying to define when these slanted faces, and when I went through the hand calcs, it just became way too cumbersome to truly solve for the value for those. So I switched to using the face because the integral was something I physically could not solve by hand. It was very long because of the nature of the equations used and the cosine for the change. It was very, very cumbersome, but I figured I'll use this to be a check of the code, that top face, to make sure that the code works. And if the code works, well, then the hard faces to solve by hand work as well. So there's no point in solving for one of those slanted faces when you can confirm your code works and the math checks out properly with an easier face like the top one. So I go through, I define the surface based on, this is when W, the Z direction coordinate, equals 1. So this surface is the body when W equals 1, as defined by this. The area is going to be the magnitude of that surface over its two parameters over the area derivative. So I start off by solving for dx over du and dx over dv. You can see then I find the cross product. The cross product gets me this. If I take the magnitude of that vector, that's our deformed area. So I went down here. I end up getting 66.51075, and you can see that surface 1 of our body, our frustrum in the code, was 66.518. So that checks out. We calculate that correctly by hand and in the MATLAB code. And this is my actual by hand calculations where I did it the first time, and then I just wrote that using LaTeX to make it neat. Similarly, for the volume, we define this top volume up here. This one's kind of the same idea, but instead of being the area over the two parameters, it's going to be the cross product of those two parameters dot with the height. Because if you think about it, right, the volume of something is really just the area times the height going up and down, and that's why it's the dot product. So we define, it's just the body calculation, then we plug in the deformation map for all parameters opposed to just 2 as before. And then we solve for the 3 derivative functions. And so that makes our integral going to be this function right here. So triple integral, these should have 1s next to them because uv and 1 are all ranged from, or uv and w are all ranged from 0 to 1. So we have the cross product of our du, or dx du and dx dv dot with our dx dw. Now this, I solved it by hand on paper on the next slide, and I got a value. I had to use, the integral was so cumbersome, I had to use an online numerical tool to make sure that I got the right number. So I took it to a point, and then I couldn't solve any further just because the algebra was so long again with the sign and all the fractions. So again, by hand, I solved for the deformation map. I showed the 3 derivatives here, and then this is where I got to with the function. So it would just be the triple integral of this function right here. All of these added together from 1 to 0, which gets you 125. I confirm with Wolfram Alpha. All right, I'm just going to show the code now, show that it works. So if I click run on it, it'll show us those 2 geometries from my results slide. Come on. There we go. There's the 2 geometries. And if we go here, we can see that surface 1 equals what we showed in the slides, and that 125 for the volume that we got. All right, thank you.